Okay, so for the constitutional isomers, it is divided into three, as you look in the flow diagram earlier. So the first is what is called is the chain isomerism, or in the diagram just now, it is written as skeletal. And then we have this positional isomerism, and the third one is functional isomerism. So for chain isomerism, the chemical formula is still the same. You have C4H10, okay, still the same number of carbon and hydrogen, but the way that all of these carbons are arranged is slightly different, in which that it can be in straight chain or branching. Okay, we have two examples over here. Let's say this one is butane with 4 carbon and 10 hydrogen. So it can be arranged this way. All of the carbon are in straight chain, while the second isomers that you can have with the same number of carbon and hydrogen is propane, but the other carbon will become substituents. Okay, and while for pentane, 5 carbons can be arranged in straight chain like this, or you can arrange in 4 carbon chain with 1 becomes substituents, or like this, whereas there you have 3 carbon in a straight chain and the other 2 become substituents. So if you look at this, as the number of carbon over here that you have become larger or increasing, then you're going to end up with a whole lot of different isomers. Okay, so if you have you have 4 carbon, you may have 2 different isomers. If you have 5, become 3, and the rest you have to how to say, determine whether it can be arranged in different uh, branching way. Then for positional isomers, so for this one, they are still in the same functional group. Like this example, you have a bromine. So this is an alkyl halide or haloalkane. So in which that the bromine could be arranged on the first carbon, or you can put it on the second carbon. Still in the same group of haloalkane, but you have one bromopropane for the first structures, and the second one is 2 bromopropane. And this is an example with aromatic compound. Both have the same chemical formula with Cl, okay, chlorine, but the chlorine could be attached to the carbon that is not on the ring, or it could be attached directly to the benzene ring. Okay, so all these three is the ortho, meta, and para positional isomers. You have 1, 2 for ortho, and then 1, 3, and at position carbon number 1 and carbon number 4. Then to the functional group isomerism, so they may have the same molecular formula, but they differs in terms of their functional group. Okay, so like earlier example, one is an alcohol while the other is an ether. So like this, I have put these 3 carbon with 6 hydrogen and 1 oxygen. So it could be an aldehyde, or it could be a ketone. Depends on how you put the C double bond O. If you put it at the end or the terminal carbon, or you place the C double bond or the carbonyl group in the middle. And for this one, okay, you have an ester and also a carboxylic acid sharing the same molecular formula. And earlier in the second chapter, if you recall, that alkene and also cycloalkane, they also share the same general formula, which is CnH2n. Okay, they also have the same number of carbon and hydrogen, but one is a cycloalkane or alkene, while the other is an alkene. Okay, different functional group. Now on to the second type. Okay, on the right side, if you refer to the diagram earlier. Okay, this is conformational isomers. So under conformational isomers, you have this isomers that is formed by rotation about the carbon-carbon single bond, and also later at the end of this unit, we will look into the cyclohexane conformation. Okay, but first, for this conformational isomers involving rotation on the carbon-carbon single bond, you must have at least 2 carbon. Okay, 2 carbon, and that carbon must be bonded by a single bond. Okay, if if there is only 1 carbon available, okay, 1 carbon available, then that means you cannot do the rotation. The rotation must be on the single bond. Okay, so if you draw in 2D, so this is considered to be 2D, you're gonna have something like this. So you have C and then H, H. So it is hard to how to say visualize or to view. So here it is said that the structure is in staggered conformation, while for this one, it is in eclipse conformation. So what is staggered and also what is eclipse conformation? This is the view from the side, okay, at an angle. We look it from the side, and this is called as the Sawhorse projection. So what you see over here, okay, this dot is the carbon, which is this one, okay, and this dot, okay, is the carbon for this side. And now you look on the hydrogen. You look on the hydrogen, you have 1, 2, 3, and this hydrogen correspond to this hydrogen, and this hydrogen. So, and on this side, if you look, the hydrogen is positioned in a way that uh, 2 are pointing up and 1 is pointing down. Okay, and when you rotate, the rotation is actually on this axis. Okay, on the axis of the C-C bond. Okay, so from what we call as this staggered conformation, now it is in eclipse. Okay, so I have to show you using this software. One moment. Because if we are in class, then I'll bring the 3D model. So right now, you guys can wait. Okay, so you all have your laptops, right? So maybe after this, you can download this software. It is called Avogadro. The symbol is this one. Okay, it's free, so you can just go and Google. In Google, just type Avogadro chemical software. So you can download this for free, or maybe if you have CamDraw, okay, you can use CamDraw 3D. That also can be used. And there is this one, MacMol, MacPyMol also can be used. Let me show you other softwares like this, Spartan or Marvin Sketch. So these are among some of the softwares that can be used to help you with this unit, okay? Because I cannot show you the 3D models, so we will use the software. So earlier, in the conformational, so there must be 2 carbon, okay? Those 2 carbon will be in the form like this. Okay, it will be in the form like this. All right. So now, sorry, wait. You guys can see, right, my screen? Boleh nampak?
Boleh.
Yeah, sekejap saya nak zoom. Okay. So, earlier, if you draw on a piece of paper, 2D, you will draw it something like this. So this is carbon, this is hydrogen, hydrogen, and hydrogen. So this is your other carbon, this is the other hydrogen. So what is the difference between this staggered and also eclipse conformation would be that for staggered, okay, if you have to view at an angle like this, you can view it at angle like this, okay, or you can also view it from the front. So if you look from the front over here, this carbon have one of the hydrogen pointing upward, while the other two to the left and the other one to the right. Okay, so if you turn this at an angle, okay, so one will be pointing up, the other one will be pointing to the left or towards the back, and this one will be pointed in front or towards you. While this other carbon, which is at the back, they still also contain 3 hydrogen, okay, 3 hydrogen, but one of the hydrogen is pointing down, okay, pointing down. Why I said pointing down? If I rotate it like this, okay, right, rotate it like this, okay, this one earlier is pointing upwards just now, right? But for the back carbon that is back, the hydrogen is downward like this, while the other two hydrogen, okay, which is this one, will still be pointing to the right and to the left, but it will be positioned slightly on top, okay, slightly on top. Now, this is what you call as the staggered conformation, in which that the carbon in front, okay, carbon in front and carbon in the back, all of the hydrogen are they are not what you call as overlap, okay, overlapping. So they are not overlap, which is like this. So you see that the hydrogen, okay, which is on the front pointing upwards, for the back carbon, it does not contain any hydrogen that is pointing upwards. The hydrogen is pointing down, okay, pointing down like this. Okay, for this one untuk staggered, clear tak? Boleh faham on the structures before we start on the rotation? Clear? Okay, so the staggered would be these two carbon, one hydrogen is this way, while for the back carbon, it is pointing down. Okay, so this is how the hydrogen is being arranged. Okay, because if you have learned into your geometry, for carbon, the geometry should be in tetrahedral. Okay, so this is how the bonds will be positioned. Now, on to the eclipse. So when it is in eclipse formation, when it is in eclipse formation, so what will happen is, wait down. Sorry. So now this is in sekejap saya lukis balik. Give me a moment. Let me sekejap ya. One moment. Let me open back the software. Okay. Saya touch present. Okay, so now what happened is let me draw another one over here. Okay. Oops. So this is from the what happened here? One moment. So this is from the earlier one. Okay, this is the staggered conformation. While for this, if you look, the difference is all of the hydrogen, okay, that is on the front carbon and also on the back carbon are overlapping. Okay, overlap. So it's like that's why the name is eclipse, like the sun eclipse where the moon is covering the sun's face. Right? The front carbon is overlapping the back carbon with all of the hydrogen. Okay, this one, the hydrogen is pointing up, and this one also is pointing up. And for the front carbon, it is on the right side. This one also on the right side, all pointing toward the same direction. Okay, so this is eclipse, while for this one, which is earlier, this is staggered. So what happened is actually to change from staggered to eclipse or from eclipse to the staggered conformation, the bond between this carbon-carbon bond, they are rotate at a 60 degrees angle. Okay, 60 degrees angle, which is this one. Okay, so another way in which that you can view the this conformational isomers is by using this Newman projection. So by using Newman projection, you are viewing the compound, okay, the compound, the C along the C bond. That means from the front, as what I have shown you, which is from this angle and also from this angle. So that is the Newman projection. While this one, okay, like this is actually from the side angle. You look maybe from this side for the structures, and maybe for the staggered, you look it at this angle, okay, at this angle. But for Newman, you view it along the C bond. That means right from the front. So this is your staggered conformation. So you have the front carbon. This is the front carbon. You have to draw it with 1, 2, and 3 like this. Okay, and the one at the back is the circle, the second carbon with all of these hydrogen. Okay, so and this one is your eclipse. So eclipse, you have your front carbon and the back carbon overlapping with all of the hydrogen as well. Okay, with all of the hydrogen as well. Later next week, I will teach you on how to draw all of these structures. Okay, I will use my iPad, okay, to draw all of this so that you know how to draw, because right now it's quite hard to show the slide and also to teach you on to draw. So don't worry about how to draw all of this. For the first part, I just want to go through all of the lecture first, okay, and maybe show you on the 3D structures using the software earlier. So then we will go into the stereoisomers. So for this one, okay, stereoisomers, it will involve this chirality just now. Okay, so whether a compound is chiral or not chiral, it will be determined under this stereoisomerism. So stereoisomers are compounds that are made up of the same atoms. Okay, they are connected by the same sequence of bonds, but having different 3D structures. So different 3D structures in a way that we look on this compound. So some structural formula, but same structural formula but differ in a range of atoms in space. Okay, so how they are arranged in space, and then this optically active substance. Okay, so under stereoisomers, they have what you call as optically active substance, which can rotate the plane polarized light. Okay, this can actually be measured using a polarimeter. Okay, in the lab, there is an instrument called polarimeter. You place your sample, or for example like this organic compound, and then we put a plane polarized light. So if it can rotate the beam of the light, so that compound would be said as optically active. And this rotation, okay, of this plane polarized light can be either clockwise or anti-clockwise. Clockwise to the right, or anti-clockwise to the left. Okay, so clockwise to the right and anti-clockwise to the left. So here is the diagram on the plane polarized light, or the polarimeter. So you have your light source. Okay, actually the light source, or the wave that is coming from the light, is coming at very different angles. Okay, there's a lot of angle. One could be on a x-axis, okay, x-axis, and this one is coming from the y-axis. So what is the purpose of putting a polarizer? Is you just only one type of light wave coming through, okay, which is from the y-axis, okay, which is coming from the y-axis. So it looks like you have the heel, you have the trough, you have the heel, okay, and so on and so on. So this is the function of polarizer. So polarizer looks like a slit. Okay, it looks like a slit. If you remember your physics, okay, you learn on the water ripple, you put a slit onto the water surface, so the wave will come out, okay, coming in from one angle only. So this is similar like that. So the light wave, okay, you only have from the y-axis. Then you're going to put your sample. So the sample is the organic compound. So this is how the organic compound can be determined whether it is optically active or not, okay, by analysis. So this is the viewer. So what the viewer will see is that this plane polarized light, okay, which is coming in from one angle like this, okay, original light source can be x-axis, y-axis, or it could be in z-axis as well. So this plane polarized light, okay, can be rotate to the right, okay, to the right like this, or it could be rotate to the left. So to the right, it is called as dextro-rotatory, okay, or sometimes we use symbol, okay. The symbol that can be used is D or plus, okay, D or plus symbol, and also levorotatory. So this one, the symbol would be negative or L, okay, D or plus, L or minus for levorotatory. So you just remember that rotate to the right is positive, rotate to the left negative. So these are for the optically active compound. But if your sample does not rotate this plane polarized light, it still remain the same, okay, remain the same like this, then that would be called as an optically inactive organic compound. So the compound is said to be optically inactive. So it is not considered to be a stereoisomer. So examples, one of the optical isomers of amino acid, okay, for alanine is known as positive alanine, while the other stereoisomer is called as negative alanine. So these isomers have the ability to rotate the plane of polarized light, will be known as optical isomers. So the word optical refers to the use of light, okay, because it can rotate the light source, okay, the plane polarized light. So that's why we call it as optical isomers. And then if the solutions are equally concentrated, okay, the amount of rotation caused by the two isomers will be exactly the same, but in opposite direction. That means if, let's say, if let's say your sample, it rotate, you can rotate to the left and you can rotate to the right, but with the same strength, that means the angle of rotation is the same. It infers that your sample contain equal amount of this positive and negative optical isomers. Okay, so this 50-50% mixture or 50-50% ratio is called as a racemic mixture. Okay, racemic mixture, or sometimes it will be called as racemate. Okay, it has no effect on plane polarized light, but the racemic mixture will not rotate any of this. Okay, if you put plane polarized light, it will not rotate, because the rotation to the left and to the right is in the same amount. Okay, because you have half positive and half negative. Okay, you have half positive and half negative, so they can kind of like cancel out each other. The rotation is like cancel out. Okay. So then we will go into this chiral and achiral molecules. So these are all of the terms that is used in the stereochemistry. So for chiral and achiral molecule, so there will be two groups, okay, the same attached to the central carbon atom, and also the molecule has a plane of symmetry. So if you look at this, okay, let's say you have an organic compound which you can cut in the middle. You can cut in the middle, cut in half, and both sides will be the exact opposite of each other. Okay, you have the left and on the right side is the same. While for this one, okay, if you look at this, you cannot say that if you cut in half in the middle, the right and the left are not the same. Okay, they are not the same. And this is one of the criteria that is needed for a compound to be chiral. Another rules is that, okay, for a compound to be chiral is that there are 4 groups, okay, attached that should be attached to this same carbon. Okay, the same carbon. Okay, later there will be examples. So another, this is chiral and achiral molecule, and now we will look into chiral center, stereogenic center, or this asymmetric carbon atom. These are all have the same meaning. Okay, it can be called chiral center, stereogenic center, asymmetric carbon atom, and it could also be called as chiral carbon. So this molecule that has no plane of symmetry, okay, will be described as chiral. Okay, no plane of symmetry, you cannot cut in half. So the carbon atom with 4 different groups attached, which cause this lack of symmetry, will be described as chiral center. So what does it mean is, if let's say you have a carbon, okay, let's say I draw a carbon like this, one carbon, but now the carbon all have, if you look at this carbon all contain hydrogen. But what if I change to maybe this one is chlorine, okay, and another one here would be bromine, and this is OH group, and the other one is remain the same, which is hydrogen. So now this carbon, okay, this one, this is the carbon, it contains 4 different groups that is attached to it. So you have bromine, you have OH, you have chlorine, and you also have hydrogen. So this carbon in the middle, okay, this carbon that I'm showing in the middle is called as the chiral center, okay, or the chiral carbon or stereogenic center, okay, because it contains 4 different groups. If let's say there is only 3, that means this one also is hydrogen. Okay, or oh sorry, undo. Okay, if let's say 2 of these are the same, you have carbon, hydrogen, and maybe chlorine, and you have this OH and OH. So if there is 2 substituents of the same group or same atom, so that carbon in the middle won't be called as a chiral center. Okay, all of the carbon must be 4 different atoms or group of atoms. So the molecule with plane of symmetry is described as achiral, which is this one. So when it contains a plane of symmetry, it will be called as achiral, while the one with no plane of symmetry, so it has the ability to be chiral. So to locate a stereogenic center, this carbon or the chiral center, you have to check the tetrahedral carbon that is available in the atom or molecule. So tetrahedral carbon is sp3 hybridized. That means the carbon would contain 4 bonds. If you see any carbon with double or triple bond, that is not sp3 hybridized. Okay, that doesn't fall into sp3 hybridization. And then once you find this carbon, okay, so you have to look at the 4 groups, okay, the 4 groups that is bonded to it, whether it is the same or all of the 4 groups are different. Okay, all of the 4 groups are different. So always omit from consideration all carbon atoms that cannot be tetrahedral, okay, such as sp2, which is double bond, or sp, which is triple bond. Okay. So example for a chiral compound. So consider this compound, which is 2-bromobutane. Okay, 2-bromobutane. So the carbon which is bound to the bromine. So where is carbon is bound to the bromine? So this is carbon number 2. So you have bromobutane 1, 2, 3, 4. 4 carbon. 1, 2, 3, 4 carbon. So this carbon, okay, this carbon is bonded to bromine. Now you are going to determine which carbon is the chiral center. So is it sp3 hybridized? So you have to check. So it contains 4 bonds. So 1, 2, 3, 4. 4 bonds. And then check whether it is bonded to 4 different groups. So you have bromine, you have hydrogen, and then you have CH3. And for this one, you have an ethyl, which is CH2CH3. So all of these are considered to be different. Okay, you have hydrogen, bromine, a methyl group, and ethyl group. So all of the other carbon in this molecule are not stereogenic centers since they are bonded to at least 2 hydrogens. So for example, like this one, even though it is an sp3 hybridized, okay, but it's bonded to 3 hydrogen. So all are the same. This carbon as well, it is bonded to a methyl group, and this whole other CHBr and CH3. But then again, it is bonded to 2 hydrogen. So same. And then this terminal carbon is the same like the first carbon. Okay, so there's only one chiral center that is available in this compound. Okay, so the chiral center must contain 4 different groups. You have 1, you have 2, you have 3, and this whole other ethyl. Okay, this whole other. So you don't just look on the atom itself, you have to look on the whole group of atom that is bonded. So this is will be considered as 4 different groups of atoms. So example like this. So identify any stereogenic centers available in this 2 compound. So first, you have to look for sp3 hybridized carbon. Okay, that means carbon that is bonded, that has 4 bonds. So when you see these 2 double bond, definitely these 2 cannot be. So these 2 carbon already considered to be not in the running, becoming stereogenic centers. And then how about this one? This contain carbon, carbon and carbon bonded to these two carbon. But then again, even though it is not shown, there are two hydrogen. Okay, it is bonded to two hydrogen. You have one hydrogen, you have one hydrogen. So this is the same case for this carbon as well. Okay, this carbon and this carbon as well. But for this one, okay, there is only one hydrogen available. Okay, there's only one hydrogen because it already contain the CC bond and then another CC bond, and this is also another CC bond. Okay, so this can still be considered. Then how about this one? So if you look, it is bonded to two hydrogen, so definitely cannot. Okay, definitely cannot. This one also cannot. So then these two terminal carbon, okay, it is still sp3 hybridized, but there is three hydrogen. Okay, three hydrogen. So also cannot be considered to be stereogenic centers. Then this carbon. So you look, oh, there's only one hydrogen. Okay, and on this side, this is the R group. Oh, so there's a possibility, but then it is bonded to two CH3 group, which is the same. So definitely, this one also cannot be the chiral centers. Then you look back on this carbon earlier, okay, which is this one. Okay, it is bonded to hydrogen. So this is your first group. And then the second group will be this whole thing over here, which is totally different than hydrogen. And it is bonded to this carbon, which is CH2. Okay, CH2. And then it is also bonded to this carbon. So is this carbon and okay, is this carbon and this carbon the same? They are not, because this is CH2 and this one is CH. Okay, CH. So they are different. If let's say there is no double bond over here, this is CH2, then that would still be considered to be the same. But now this is CH2 and this one is CH. So this is not considered to be the same. So the carbon in the middle over here is bonded to four different group of atoms. So this can be considered as the chiral center. Okay, chiral center. Okay, normally you mark it using the asterisk symbol. Okay, like this. And then for this second example, so for the second example, this one is CH3. Okay, the last carbon also cannot. We remove that first. Okay, and then how about this one? This is carbon bonded to bromine and also bonded to another CH2, but it also contain two hydrogen over here. This one also two hydrogen. This one also two hydrogen. So all of these cannot. Okay, all of these cannot be stereogenic centers. Then how about this carbon? So you have chlorine, you have CH3, okay, and then don't forget it is also bonded to one hydrogen. Okay, in skeletal it is not shown. Then what is the other group? Which is this one. Okay, which is this one. So four different group. So this would be your chiral center. Okay, this will be your chiral centers. So chiral compound are optically active, while achiral compound or non-chiral compounds are optically inactive. Okay, so this is the carbon that is chiral center, and this is the carbon that is chiral centers. Okay, any question setakat ni on how to determine chiral center? Semua clear tak? You just have to find the carbon that is bonded to 4 different atoms or group of atoms. Okay, so find the carbon that is bonded to 4 different atoms or group of atoms. So atoms is like this, chlorine. Group of atoms, for example, like CH3 or this whole other carbon chain. Okay, carbon chain.
So,
Yes.
nak tanya, apa beza optically active dengan optically inactive? Macam apa kepentingannya dalam
Apa kepentingannya? So,
macam kenapa kita nak tahu aktif atau tak aktif?
okay. So kalau tadi dah tahu kan macam nak tahu dia aktif atau tak aktif is by doing the plane polarized light. So if it's rotate, it can rotate to either left or to the right side, then it will be optically active. Tapi kalau dia tak rotate, then optically inactive. But why do you want to know? Because for what do you call that, drugs, okay, this optically active and inactive, okay, this is I'm talking about when related to your field, which is pharmacy and pharmaceutical. So certain drugs is needed in a way that it should be either in this R or S configuration. Actually kita tak masuk lagi. So once it is optically active, there will be 2 type, which is the one that can rotate to the left, okay, which is tadi kita tengok yang example alanine kan, ada positive and negative. Okay, sometimes for drugs to be useful, it needs to be one of these stereoisomers. Okay, dia perlu menjadi salah satu daripada stereoisomers ni. For example, macam omeprazole. Okay, pernah dengar omeprazole? It is a proton pump inhibitor. Biasa orang gastrik lah. Kalau you pernah gastrik, you go to the clinic and the doctors will prescribe you with omeprazole. So the normal omeprazole that you eat will contain both stereoisomers. Okay, the positive and the negative. It can rotate to the left and to the right. Okay, but sometimes the doctors will prescribe you with esomeprazole. Okay, esomeprazole ni, it only contain one of these stereoisomers, which is the left. Okay, the one that can rotate to the left. Because some patients, when they consume the normal omeprazole, dia tak ada effect. Okay, there's no effect. Mungkin dia dah immune ke, I don't know, something like that. But then again, the doctors will prescribe these certain chiral drugs, okay, in order to treat the disease. Tu example lah, contoh macam omeprazole. So there are many other types of chiral drugs that is available, okay, in which one of these stereoisomers will be useful while the other one could be harmful. So that's what is to say the relevant of knowing whether it is optically active and optically inactive. Kalau you mix, let's say if both side, the positive and negative is useful to treat, or the one is useful and the other is harmless, kalau you makan pun tak ada apa-apa, then that will be alright. But for some, the positive will treat you while the negative will have adverse effect. So definitely we want to remove all of the other the negative stereoisomers first before it can be made into the formulation. So that is why we need to know whether a compound is optically active or optically inactive. Kalau dia optically inactive, then there will be only one type. Dia takkan ada 2 stereoisomers. There will just be only one. Okay, so that's why it is important to know whether a compound is optically active or not, particularly in pharmaceutical, okay, pharmaceutical drug formulation. Okay, alright, is that explanation? So now we will go into this chirality. Okay, so earlier you have determined whether that carbon is a chiral center or not. So why it is important, what is the importance of this chirality? So this is an extremely important concept in biological sciences or maybe in biochemistry. Okay, so biological systems are all chiral. That means it will accept only one type, okay, between the stereoisomers. So for example, like sugars, amino acid, enzyme, and proteins, they are chiral. Yet only one enantiomer will ever be used. Okay, so the word enantiomer refers to the optical isomers just now, which is, okay, this is the optical isomers. So it can also be called as enantiomers as well. So these enantiomers, only one of them will eventually be useful. So the other enantiomers usually has altered biological properties, or it could be toxic altogether. Okay, so sticking the wrong enantiomer into an organism is like sticking your left hand into right-handed glove. So imagine it use the same concept, which is lock and key. So the structure like this is very specific. It has the same, the arrangement is like this, but then it has to go into the binding site. Okay, in our body normally, for example, when you eat a drug, so the drug will contain the chemical compound, and the drug will eventually, let's say it needs to kill a bacteria. So on that bacteria, there will be a binding site which is coming from the protein of the bacteria. So that drug will have to bind, okay, on this side of the receptor, and the side of the receptor will only accept specific shape. Okay, or will only accept specific shape. For example, like this, the square should be on the left side. So if the compound that is coming in, the square is on the left, you cannot fit. So this would be considered as the positive in optical isomers, and this one is the negative optical isomers. So that's why it is important that you know which of these enantiomers works, okay, so that you can separate them. Okay, so all of these structures, okay, it can be represented, okay, in 4 different structures. So this is how you can draw on a piece of paper. Okay, you cannot use softwares all the time because you have to write and draw on a piece of paper. So how to show that this carbon and hydrogen and all of these atom that is attached to it with 3D configuration. So there are the first one, which we call as the wedge dash structures, okay, and then you have Newman projection that we have seen earlier, and this is Fisher projection. Okay, it looks like a fish bone. Okay, and we also have this sawhorse projection. So what is the difference? So for flying wedge dash like this, it is best when there is only one chiral center available, which is this carbon in the middle, okay, or this carbon in the middle. So you can use this wedge dash when there is only one chiral center. Okay, so if there is only one chiral center, straight away use this type of representation. Okay, next week I will tell you on how to draw all of this. Okay, don't worry. Then Fisher, which is this one, is best to use when your compound contain more than 2 chiral centers. Okay, at least they must be 2 or 3 or 4. You can use this Fisher projection. While for Newman and Sawhorse, the chiral center that is it is limited to structures with two chiral centers, okay, which is carbon number 1 and carbon number 2. Okay, this carbon number 1 and carbon number 2. So two chiral centers, one chiral centers feature two or more chiral centers. Okay, so you need to know which projection or representation to be used when drawing the structure of the stereoisomers. Okay, stereoisomers. Now on to the term, okay, of enantiomers. So enantiomers are actually optical isomers. Earlier we have determined how are you going to determine whether a compound contain optical isomers or not by doing the plane polarized light test. So if it can rotate to the left, it will be level rotatory. If it rotates to the right, that will be dextrorotatory. So L and D. So these two optical isomers, they will be mirror image to each other. Okay, they are mirror image to each other, and they must be non-superimposed. That means it cannot be overlapping. For example, our hand, okay, our hand is an example of enantiomers. So your left hand and your right hand is mirror image to each other, okay, mirror image. But when you place one on top of the other, they are not superimposed. You don't turn the other one and then don't do your hand like when you want to clap. Okay, so that is superimposed. But the direction remain the same. Okay, both side to the up like this, and then you place your right hand on your left hand, and then maybe try to put your left on the right. So this is called as non-superimposable. Okay, you cannot overlap them. So this is one of the properties for enantiomers. Okay, they must be mirror image and not superimposed. Okay, cannot superimpose. So enantiomers will have the same physical and chemical properties. Okay, same physical and chemical properties, but differs in their physiological functions. That means, let's say once you eat the compound, the left hand will give you different effect and the right hand will give different effect. But the physical and chemical properties are exactly the same. Example, like this, we have butanol. So earlier in the second unit, we have learned on how to draw the structures of butanol or 2-butanol. So from here, you know that the position of the OH is at the second carbon. So for this case, the choice of projection to be used is the wedge dash projection. Okay, the wedge dash projection, in which that the carbon that will be the chiral center will be drawn in the middle. Okay, it will be drawn in the middle over here. So that will be your chiral center. Then from this is where you are going to draw all of the other groups or atoms that is attached to it. So the second carbon, you know that this is the second carbon. So the second carbon would be the chiral center. It is bonded to the OH. It is also bonded to the CH3 and the rest of the alkyl chain. Okay, so you have 1, 2, 3, 4 still butane and also one OH group. So butanol and the OH is at the second carbon. So this is the wedge dash representation. Now, if you draw a mirror, let's say there is a mirror here, the opposite image would be you have C, okay, the one on top is still the same, but the hydrogen is now pointing to the left. This one is to the right. So now it is pointing to the left, and CH3 from pointing to the left, it is now drawn pointing towards the right. Okay, so this is a mirror image, a mirror image. So if it contain a mirror image, okay, this will be considered as a pair of enantiomers. Okay, a pair, pasangan enantiomers. Then the second example, so this one, you have bromine. This is alkyl halide or haloalkane. You have the same carbon in the middle. Okay, same carbon with CH3 and CH2CH3. If you look that the position of this CH2, CH3 or CH3, it depends on you. You are the one who are going to draw it. You can place this on top, or you can place CH3 down here. Okay, so let's say this is the structures, and this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. So still 4 carbon, butane, and the bromine is at the second carbon. So 2 bromobutane. And if there is a mirror over here, the mirror image of this structure would be, this one will remain the same, but the CH3 earlier on this structure, it is to the right, sorry, to the left. For the mirror image, it will be pointing to the right. Okay, so you just make the position opposite. Okay, opposite. So this also have a mirror image. And what you have to do is, you also have to take this image and superimpose. Take this one and then superimpose on top of the other mirror image. If it is not superimposable like this example of your hand, this will be considered as enantiomers. Same as well. If let's say it can be superimposed, okay, the mirror image is superimposed, that means it will not be considered as a pair of enantiomers. Okay, the rules must be the mirror image of the structures is not superimposable. That is one of the criteria for becoming an enantiomers. So what is the number of isomers, what they call that, permissible, depending on the number of chiral centers. So for molecule with multiple chiral centers, that means more than one. If there is only one, there will be 2 enantiomers only. But let's say you have 2 chiral centers. So the number of possible stereoisomers will be given by this equation. So x equal to 2 to the power of n. So n is the number of different asymmetric centers or these chiral centers. So let's say if you have 2 chiral centers, so this is Fisher projection. Let's say if you have 2 chiral centers over here, that means you will have 4 enantiomers altogether. Okay, you have 1 pair and another pair. If let's say you have 3 enantiomers, then 2 to the power of 3, that would be 8. So there will be 8 enantiomers, 4 pair. Okay, so it depends on the number of enantiomers. So like this is in Fisher. You can check whether it is enantiomer or not. This is the chiral carbon. You have CH3, you have NHCH3 over here, hydrogen, and this whole other group. So this carbon is chiral. And for this carbon, it is bonded to benzene, hydrogen, OH, and this whole other group. So that would be considered as the chiral centers. And then you put a mirror. If the mirror image is not superimposable, then it will be considered as enantiomer. So 4 optical isomers or 2 pairs of enantiomers. Then the stereochemistry of tartaric acid. So example, I'm using tartaric acid as example over here. So tartaric acid has 2 similar asymmetrical carbon atoms. So that means it has 2 chiral centers. So which one? So you have C over here, and this is COH. You have hydrogen, you have OH, and this whole other group. So this is chiral center. And for this carbon, hydrogen, OH, COH, and this whole group as well. So chiral center, chiral center. So the D and L tartaric acid are a pair of enantiomers. So these 2 are a pair of enantiomers. So each molecule is asymmetrical. Asymmetrical as in, if you place a plane of symmetry in between, the left side or the right side cannot be superimposed. And if you put a plane like this as well, plane of symmetry, you can cut in half or you can cut in half this way. It is still not the same. Okay, so then you also have this third one, which is meso. Okay, meso tartaric acid. So in this meso tartaric acid, it still contain two chiral centers. Okay, this one still contain two chiral centers. You have C. This is one chiral center, one hydrogen. You have OH group. You have COH, and this whole other group of atoms. So and for this one, OH, hydrogen, COH, and this whole other group of atoms. So both of these carbon are considered to be chiral centers, but the molecule is symmetrical and does not exhibit optical activity. So how can it be symmetrical? Okay, from these two D and L, if you cut like this or you cut this way, okay, it is asymmetrical. But for this structure, if you cut along the y-axis like this, it is not symmetrical because one side on the left you have hydrogen, on the right you have OH. But you can cut in half in x-axis. So if you put a line over here, okay, a mirror, for example, plane of symmetry on this side. So the one on top and the one below are exactly symmetrical. Okay, you have carbon, carbon, hydrogen, hydrogen, OH, OH, COOH, COOH. Okay, so this internal symmetry, okay, cause the structure to be optically inactive. Okay, so the optical activity is internally compensated. So that means it's like it cancel out the top part of the structure. Okay, cancel out the optical activity of the second chiral center. And the effect of one asymmetrical carbon atom balancing the effect of the other. So meso compound or mesoisomer is a chemical compound with molecules that contain two or more, okay, chiral centers, but it is optically inactive. Okay, optically inactive because it contains this internal plane of symmetry. So this is the definition for a meso compound. And an example that you can use is this structure of meso tartaric acid. Okay, tartaric acid. So for tartaric acid, contain the normal pair of enantiomers. So these two are a pair of enantiomers, while this one is a meso tartaric acid. Then this last term for today, okay, diastereomers. So what is a diastereomers? Okay, earlier we have enantiomer, meso compound or mesoisomer, and this is diastereomers. So this is when you have, okay, stereoisomers which are not mirror image of each other and non-superimposable. Okay, what does it mean? So a pair of optical enantiomers like this, D and L, okay, they are enantiomers. So they are called enantiomers. But then again, this mesotartaric acid is also a type of stereoisomers. Okay, it's still considered to be stereoisomers. So this pair of D tartaric acid, L tartaric acid, and this meso tartaric acid, which is the third one, which are not enantiomers, they are called as diastereomers. So when you compare number 1 and number 2, okay, when you have number 1 and number 2, they are called a pair of enantiomers. But if you have number 1 over here, D and meso tartaric acid, they are not considered enantiomers, but they are called diastereomers. Okay, it is the same as well if you take structure number 2 and compare with number 3. So these two are considered to be as the diastereomers. So diastereomers are not mirror image with each other, okay, and also they are not superimposed. So if you put a plane of symmetry or a mirror, this structure number 2 and number 3 are not mirror image, and even if you want to superimpose or overlap them, you cannot as well. Okay, but for number 1 and number 2, it is mirror image. Okay, number 1 and number 2 are mirror image but non-superimposable. But for 1 and 2 with number 3, they are not mirror image and also non-superimposed. So that is how diastereomer is determined. Okay. So the properties of diastereomers, okay, they have different physical and chemical properties. So unlike enantiomer earlier, enantiomers both D and L are having same physical and chemical properties. Okay, but diastereomers different physical and chemical properties, different melting point, boiling point, solubilities, and in fact, they react differently as well when mixed with reagent. So that's why it is easier to separate diastereomers compared if you want to separate D and L enantiomers. Okay, so yeah. All right, so I will stop until this part. So any question? So you can ask question, boleh tanya. I'm sure you have question.